I I think it's recording, but it okay.
Yeah.
Okay. So hello everybody. Welcome back. So today we have the third lecture by Professor Horatiu Nastase, right? So I hope those who missed the first two lectures already watched those videos, right? So last time we did some non-trivial examples of AdS CFT, right? And we saw original heuristic derivation of AdS CFT by Maldacena, right? So then we did some some Witten construction, right? So we saw some Wilson loops, and then we saw the application of AdS CFT at finite temperature, right? So the black hole thermodynamics. Okay. By the way, all these things can be found in Horatiu's first book, Introduction to AdS CFT. It's beautiful. And if you are in a hurry, you don't have to read the all 500-page book. At the end of each chapter, he has highlights of the chapter, right? So you can read that. It's like a Cliff Notes version of each chapter. And among other things, he has written many other books too, right? So he was so modest that he didn't mention any of them. So the first one is AdS CFT, then application of string theory to condensed matter physics, and application of string theory to cosmology. And he also has books on classical field theory, quantum field theory, and most recent one being quantum mechanics, right? All of them have this summary at the end of the chapters. So you can learn everything in like 10 like maybe 1 hour, and then dig deeper for another 1 year or so, I guess. Okay, so with that said, Horatiu, please go ahead.
Thank you for the introduction. So today in lecture 3 we'll talk about generalizations of the AdS CFT correspondence called gauge gravity dualities, and then a kind of specific subset of AdS CFT correspondence in a certain limit that I'll describe, called the PPY correspondence and resulting spin chains. So to sort of review a little bit last lecture. So in the first lecture, we've seen that if you want perturbative quantum gravity, in order to remove some infinities, you have to go to supergravity. And in order to obtain a theory that is finite at each loop, you have to go to string theory. There's no choice, really. This is perturbative. Then we've seen we've seen another application of string theory, which has a different point of view. So instead of trying to find a fundamental theory that includes quantum gravity, now we want to use string theory as a tool to describe complicated field theory problems. But we will actually see that this is more than that. It can be used also in the opposite direction, in principle at least, namely as a tool to find quantum gravity from field theory. So let's remind ourselves a little bit what we did. So we started by describing these ND3 branes, which are three-dimensional walls plus time. So we describe them from 2 points of view: as gravitational solutions, extremal p branes, and then as endpoints of open strings. So this equivalence given by Polchinski, taken in some decoupling limit, gave us the AdS CFT correspondence, which was an equality between n equal 4 in the original formulation, between n equal 4 super-Yang-Mills with gauge group SUN in a Hopf limit with G squared n kept fixed but actually large, with string theory in a background of AdS5 process 5 type written here. So this correspondence is a duality, meaning when one side is perturbative, for instance, what we were mostly interested in and how this was derived was weak gravity, Then the other side is non-perturbative, meaning, again, in this original case, large soft coupling in the quantum field theory. But in principle, there are three possible versions of this AdS CFT. The weakest version, which was argued for in the original paper of Maldacena, was that this is only valid in the limit where G string, or correspondingly G squared Young-Mills, because you have this relation G squared Young-Mills is 4 pi G string. G string goes to 0 and GSN is fixed and large, in which string theory is approximately supergravity. But then in principle, alpha prime and G string corrections might disagree. That's one possibility. A stronger possibility is that the theory is valid at any lambda, at any soft coupling, so any G string n, but only in the G string goes to 0 limit and n goes to infinity, which would mean that alpha prime corrections might agree, but not G string corrections. And finally, the strongest version, which is now believed to be correct after a huge amount of tests, is that the duality is actually valid at any string coupling, so any, or equivalently, any G Young-Mills, and any n, so equivalently any G string and alpha prime. Well, if that is so, then we note that when lambda, the soft coupling G squared n goes to 0 and n is small, we obtain on the other side quantum gravity. So in principle, this gives us a handle on quantum gravity. So we had the original AdS CFT of Maldacena, but this was generalized. First of all, it was generalized to other maximally supersymmetric conformal cases. First, in the original paper of Maldacena itself, AdS 7 cross S4, AdS 4 cross S7. And these backgrounds in general are called gravity duals. And these systems were obtained also from decoupling limits. In the case of these backgrounds for NM2 branes and MM5 branes in M theory. But then also people gave up conformal invariants. So they gave up either supersymmetry by taking AdS cross another space, for instance, by dividing these sphere by a finite group gamma, or breaking even conformal invariants, meaning replacing the AdS space, since the AdS space corresponds to conformal invariants. So in field theories, we're usually interested in theories with some mass gap. And how is that obtained? Well, you have to turn AdS space into something like a finite quantum mechanical box. And the way you do that, you remember AdS is like an infinite cylinder. And if you cut out a thin cylinder from the middle of this AdS cylinder, then that effectively turns AdS space into a quantum mechanical box or resonator with only discrete modes and therefore with a mass gap. So I've written for you the metric in here in terms of some U, which corresponds to an energy scale in field theory. So if you want to have a mass gap with a minimum energy, then you have to have a minimum distance, r. Moreover, motion in this U would correspond to renormalization group flow in the quantum field theory. Okay, so if I am interested in simulating QCD, which was the original goal of AdS CFT, what would I need? Well, I need a large N quantum gauge theory, remember, n goes to infinity corresponds to small string corrections, small quantum string corrections, this string. Then how do I define where the theory lives? Well, originally, people, at least in AdS, in the AdS case, people said, well, the boundary at infinity is where the theory lives, holographically. But if you don't have an AdS space, you have something more complicated, then one can say is that since the energy scale U corresponds to a position R in the gravity dual, then that's really where the theory lives when we're talking about some energy. So you need a gravity dual that has one dimension more than the field theory. And then, as we said, the mass gap corresponds to a minimum distance in this gravity dual. And it's important to realize that the gauge group in the field theory does not appear in the gravity dual. It only appears through this number n, but there's no gauge group anymore. The gauge group is gone itself. There's no more redundancy in the description. So what does the map from the field theory to the gravity dual correspond to? Well, the field theory has some global symmetries. These global symmetries become gauge symmetries in the gravity dual. And finally, if we think of the gravity dual in d+1 dimensions as being reduced on an extra dimensional space, like in AdS5 cross S5, we had an S5. If we reduce on that S5, then those gauge symmetries become global symmetries of the compact space. So to summarize, the global symmetries in field theory correspond to global symmetries of the compact space and are therefore geometrized. Then also, if you think of translational invariance as an example, then that corresponds to diffeomorphism invariance in d+1 dimensions. As I said, G string corresponds to G squared Yang-Mills with divided by 4 pi. And gravity dual fields correspond to gauge invariant operators. Hence, the gauge group is not relevant anymore, right? There's no redundancy anymore. And so we say that supergravity fields in the gravity dual correspond to super Yang-Mills operators, which are made of adjoints. But if I want something like quarks, like fundamentals of the gauge group, and also some global symmetry group, then this would correspond to introducing in the gravity dual also some vectors, some super Yang-Mills. So roughly speaking, then we would say if you want something like pion fields, which are bilinears of quarks, then in the gravity dual, this would correspond to something like super Yang-Mills fields. So summarizing then, supergravity modes in gravity dual correspond to something like glue balls, whereas super Yang-Mills fields in gravity dual correspond to something like mesons. And you might ask about the mass spectra of these guys, of glue balls and mesons. And the mass spectra correspond to mass spectra of the wave equation for various supergravity modes and super Yang-Mills field modes. All right. Now, I talked about glue balls and mesons, which are two types of gauge invariant objects, but then there's another type, namely baryons, like the proton and the neutron. So those are made of more than two fields. For instance, in the baryons in QCD and for SU3 are given by 3 quarks contracted with an epsilon tensor. But if you think of them not as field theory operators, but rather if you think of them in something like the Skirm model, they become rather solitonic. They become topological solitons. So the baryons can be thought of some sort of solitons. And correspondingly, in the gravity dual, you also have some solitons. The soliton types are some branes wrapped on cycles, I know, a two-dimensional surface wrapping a two-dimensional sphere, for instance. And finally, the wave functions for the states in the field theory correspond to wave functions for fields in the gravity dual. So it's just that in the gravity dual, we have more coordinates. So we have at least one more, the radial coordinate, and perhaps more like for the S5. So besides the e to the ikx for field theory, we also have some other wave function for the other coordinates. All right. So what are the general properties for the QCD-like theories then? So QCD has not been obtained yet, but QCD-like or SQCD-like theories. Well, if you go at sufficiently high energies, everything looks conformal because mass is become irrelevant. So translating that into gravity dual, when U goes to infinity, since U corresponds to energy, we get AdS 5 cross S5. Could be some subleading corrections to it. On the other hand, if you go at low energy, you have a mass gap. So as we said, the gravity dual must terminate at some U minimum, such that the U squared that appears in front of dx squared remains finite. And then if I want fundamental quarks, we said we want some span mills, or in other words, open string modes on some brane in the gravity dual. So that's how I introduce these open string modes or span mills, is by introducing some brane situated in the gravity dual. But the brane could be fixed or not, or could be a probe brane, which doesn't do anything to the gravity dual. These are two possibilities. And then finally, since QCD-like theories have global symmetries, if you think of QCD, you can say you have the SU2 isospin, for instance. Then the gravity dual should have something similar. So XM, the compact space of the gravity dual, should have the same global symmetry. Okay, good. So I've given you a very short description of what people want to do about when trying to construct QCD and a corresponding gravity dual for it. Once again, this has not been done yet. Even n equal 1 supersymmetric QCD is not done. It's just n equal 1 supersymmetric Young-Mills plus extra stuff, which you cannot get rid of. But in principle, if you want something like QCD, that's what we want to do. But the observation is that in all of the previous examples, we have a top-down kind of philosophy. Namely, we have a system of branes in some decoupling limit, and that gives some well-defined or heuristically defined, derived, holographic map between some quantum field theory and some gravity dual. And as I said, the hope is that one will find this for actual QCD, so with a gravity dual for QCD from some system, the system of brane in a decoupling limit. However, people started to realize that this is not necessary to have this top-down construction. Meaning people have argued for a long time and found lots and lots of tests for that gravity is always holographic. So including black holes in general relativity also introduce some sort of holography with respect to the space around it is projected onto the surface, something known as the membrane paradigm. And furthermore, if you consider anti-de Sitter asymptotics, you have, on one hand, a finite time to get to the boundary on where QFT sits, which means you could project the physics over there in a finite time. And B, you have the fact that the symmetry of anti-de Sitter is equal to the conformal symmetry in Minkowski, and both of them are SOD, 2. So then came the idea of bottom-up constructions, meaning phenomenological ones. You construct a gravity theory in AdS, not from any brain system, not derived by anything. You just state that, well, I have some gravity theory with some Lagrangian with an AdS background, and see if the phenomenology that you obtain from the corresponding field theory fits something that we want. So this was applied a lot in the case of condensed matter. And this came under the name of anti-de Sitter condensed matter theory, AdS-CMT. So there, one also has some sort of top-down description, but a little bit different than the top-down for QCD. Namely, you take some known duality, and now you try to see if the physics of the QFT matches anything you see. So in the case of something like QCD, you wanted to obtain just QCD. So just the theory, the fundamental theory. But in condensed matter applications, even the top down, you just want to see if the physics of the known quantum field theory matches anything. On the other hand, there's also the bottom-up construction, meaning, as we said, we just construct a gravity theory in AdS. You just write a Lagrangian with AdS background. And then given the holographic map, this would tell you some wanted properties for the field theory, even though you don't know the field theory. But the holographic map tells you some properties for it. So you want some properties and you construct a Lagrangian such that it has the dual field theory should have these properties. And then you calculate some others that you don't know to have some predictive power. All right, so let's see a few examples of that just to see what I'm talking about. So one example is the gravity dual of Lifshitz points. So condensed matter theory is usually non-relativistic. So one way is to construct a non-relativistic gravity dual, which would mean either gravity itself is non-relativistic, or rather, more commonly, that the gravitational background is non-relativistic, meaning doesn't have relativistic symmetry, Poincare symmetry. So for instance, one thing that is often obtained in condensed matter theory is so-called Lifshitz scaling, where space and time scale differently. So you scale time with lambda to the z, where lambda is the scaling of x. And z is called dynamic critical exponent. So one model example for that, with specifically with z equal to 2, is this one here, right? You have the first derivative with respect to time on phi, but the second derivative with respect to space on phi. So then you write a phenomenological gravity background for Lifshitz scaling, which is just invariant. So you write a gravity dual, which is just invariant under this Lifshitz scaling. So you write this metric where dt squared is divided by u to the 2z, and dx squared and du squared are divided by u squared. And so this has Lifshitz scaling. So t scales like lambda to the z, whereas x scales like lambda. And now also u, since it's also a coordinate of the gravity background, scales like u. And for this scaling, you write the generator or killing vector d written here. And then you can write the other symmetry generators, rotation generators, translation generator, and time translation generator, and commute them and find the algebra, and you find that you obtain the Lifshitz algebra. So this was just a way to obtain the Lifshitz algebra from a gravity dual, right? That was the only property that I was interested in. One can do this not just with Lifshitz algebra, but also with conformal Galilean algebra, algebra. So these are larger algebras. So besides the generators from before, one also has a particle number or conserved rest mass. That's called n. And also Galilean boosts, right? Not just rotations, but not boosts, but Galilean boosts. In the case z equal to 2, which is actually this model example from here, there's a special conformal generator C, and one obtains an even larger algebra called the Schrödinger algebra, which is the algebra of the symmetry of the Schrödinger equation of a free particle. And so for these cases, one can write a gravity dual. It's just that in this case, one needs 2 extra dimensions instead of 1, as is usual. So extra dimensions is u, the standard one, but there's also a psi. And the gravity dual is written here. So I've added to the previous one this extra term, 2 dt d psi over u squared. And that means that this is not time reversible invariant because of the dt d psi. But it's also actually non-singular. It's conformal to a plane wave. And you can check that it's invariant under a scaling as before, but now a scaling also of psi with lambda to the 2z. And then you find, therefore, that the generator D is modified for this D for scaling, dilatations. And then again, commute the generators and find the corresponding algebras. So again, this is another example of a gravity dual for which all we want to obtain is a certain symmetry algebra in the field theory. But that's deep, right? Because remember, the point about AdS was that it corresponds to conformal symmetry. So the symmetry group of AdS is the conformal symmetry at the boundary. So yeah, in this case, we do something similar for these non-relativistic algebras. But let's see also another example, which is more akin to what we think when we say phenomenology of field theory. So the holographic superconductor, which is found first by Gubser and then slightly afterwards by Hartnoll, Herzog, and Horowitz. So we want to describe a superconductor, high temperature superconductor, actually. And since we want to be near the transition point between the phases, there we know we can have a conformal field theory, so that corresponds to an anti-de Sitter background. Superconductor means charge transport, which means we have to have a current for some conserved U1. And that's dual to some gauge field in the gravity dual. We want temperature, so the temperature is dual to black hole, like we saw last time. And finally, the most important part, we want symmetry breaking. Remember, superconductor means symmetry breaking according to Landau theory. So symmetry breaking means that some operator must have a wave, again, corresponding to Landau theory of phase transitions. With the standard superconductor with rotational symmetry, so S-wave superconductor, then the corresponding operator is a scalar, so it couples to another scalar, and this should be charged, meaning coupled to the current. So the Lagrangian for the gravity theory then is kind of well defined. You have gravity with an AdS background. You have the Maxwell term. You have the charge scalar. And the charge scalar has a mass and some potential. The details I will not describe. Those are also important, but it's too much information. But so the only thing that it's important to describe is that we want that the scalar becomes non-zero near the horizon, below the critical temperature, where we have the non-zero VEV, and is zero beyond above the critical temperature. So Gabser wrote then gravity dual, which is just an anti-de Sitter Reissner-Nordstrom, meaning mass and charge, electric charge, black hole, written here. And within this anti-de Sitter Reissner-Nordstrom, you put a scalar as a probe in the background, meaning at the boundary, it goes to zero, like 1/r, but it goes to zero in a specific way with 1/r with a coefficient and 1/r² with a coefficient. And then you find that both of these perturbations are normalizable, correspond to some states. And then through the AdS CFT map, we find that the VEV or condensate of the operator dual to psi is related to these psis. And then you obtain really that this thing goes like 1 minus square root 1 minus t over tc, as the Landau theory says it should. So at least, I mean, there are more important part, why, you know, how is this possible? Why is it a high temperature superconductor as opposed to a low temperature and so on, blah, blah, blah. But those are more complicated. I just want for you to see that in this case, you obtain the phenomenology of Landau theory for a superconductor on the boundary. Okay. All right, so this was about gravity duals. Now I want to switch gears to another application, which is a certain limit that we will do on AdS CFT, in which we will see actual strings. Why so? Because, well, in the end, so we haven't reached that, but in the end, ideally, if I want to talk about quantum gravity in the gravity dual, I should see strings. We said when we reach the quantum gravity scale, we see strings. So how do we obtain that? So this was done in a paper of mine with David Bernstein and Juan Maldacena in 2002. And it's based on the idea of a Penrose limit and the PP waves that correspond to this limit. So this PP or parallel waves in a flat space background are written like this. So the non-trivial part besides the flat background is a function h of x plus and xi multiplying the x plus squared. And the cool thing about this is that this is one of the very few examples in GR where the linearized solution is exact. And that's because the only non-trivial Ricci tensor is R++, and it's d squared h. So that's, you put the Einstein equation will reduce to d squared h equals to something, which is a linear equation. And so these are general PP waves, but we're interested in ones that are not localized in X+, so they're independent of X+. So in particular, in supergravity, in 11-dimensional supergravity, we have a solution in which d squared h is proportional to some scalar quantity, which is well, this 3-form squared, so phi star phi. In general, if I write h as a quadratic form, then d squared h equal to phi squared results in 2 times trace this quadratic form is phi squared. And those are solutions with a half supersymmetry. But there's a unique solution that has full supersymmetry and has a specific quadratic form written here. And similarly, in 10-dimensional type 2b, there's also a solution, a PP wave solution with h being a quadratic form, and general solutions have 1/2 supersymmetry, but there's a unique one with a full supersymmetry with a specific quadratic form written here. So we have both in 11-dimensional supergravity, that is M theory, a unique PP wave with full supersymmetry, and in 10-dimensional type 2b, a unique PP wave with full supersymmetry. So those things must be important, and we'll see shortly why. So Penrose wrote a very interesting theorem that became known as the Penrose limit theorem. It says that near a null geodesic in any spacetime, in any metric, the spacetime becomes a PP wave. And the way this happens is that the null geodesic is defined by putting some light-like direction v to 0, and then also the transverse coordinates to 0. And then the parameter along the PP wave is the other light-like coordinates u. And then he showed that you can always put the metric in this form, written here. And then take the limit where, as we said, u is the parameter along the geodesic, so it's unchanged. But all these other parameters are scaled such that in the r going to infinity limit, they go to the null geodesic itself. Namely, v is scaled with 1/r squared, and the transverse coordinates with 1/r. So in this, it's really easy to see that in this limit, you obtain a so-called PP wave in so-called Rosen coordinates, and after some coordinate change, you get to the previous so-called Bringband coordinates. So let's understand a little bit more physically, what does the Penrose limit mean? So what does it mean going near a null geodesic and seeing a PP wave? Well, one way to think about it is that you can boost along some direction x, and then simultaneously take the overall scale of the metric to infinity. So if you take a boost, like in here, then the light-like coordinates, v, which is x minus t, and u, x plus t, get rescaled. So v with e to the minus beta, and u with e to the beta. So if I scale all the coordinates, so I have this boost, and then I also scale the coordinates by 1/r, and then I identify e to the beta with r, and take that to infinity, then I get exactly this scaling above. U is unchanged, V scales with 1 over r squared, and Y, the other coordinates with 1 over r. So that's the idea. You're boosting along some direction and take the overall scale to infinity at the same time. All right, so let's do this for AdS5, AdS5 cross S5. So let's consider a particular null geodesic, which is a null geodesic that is moving along, so moving at the speed aligned along an equator of the S5. And it also stays, the equator being defined by theta equal to 0. And then also stays at the center of the AdS5 cylinder, which is defined by rho equal to 0. And so for this one at the center of AdS5 and moving on the equator of S5 defined by theta equal to 0. So I just expand the AdS5 cross S5 metric around this rho equal to 0, theta equal to 0. I've written the metric here in particular coordinates, global coordinates, and expanded around rho equal to 0 and theta equal to 0. And after a redefinition, after defining the null coordinates, that tau plus psi, and the rescaling in the Penrose theorem, I get this PP wave, which happens to be exactly the maximally supersymmetric PP wave of 10-dimensional type 2B supergravity, which is not surprising because the only other two backgrounds that are maximally supersymmetric are Minkowski and AdS5 cross S5. So the PP wave must be a limit of AdS5 cross S5. All right. But now the more interesting and physically challenging story is what happens on the other side, on the field theory side of AdS CFT. So this was done, as I said, by myself with David Bernstein and Juan Maldacena in 2002. And we have seen that this is a limit of large R charge in the field theory. So if we consider J as we've seen, J is a rotation along an angle psi along the equator of S5, and this angle psi corresponds to a rotation of two Euclidean, two Cartesian coordinates, x5 and x6. Then in the field theory, this J would correspond to some U1 inside the SO6 R charge that rotates the 6 scalars. And so in particular, it should correspond as here to the rotation of the scalars corresponding to x5 and x6. And then energy corresponds to conformal dimension in the field theory, so math conformal dimension of the fields and operators. So then, if I construct P plus and P minus, which are the relevant quantities in the gravitational dual, then and I also consider the rescalings that I've taken with 1 over r. So these are combinations of d tau and d psi, and with a rescaling of 1 over r. I see that P minus up corresponds to, after a final rescaling, yeah, doesn't matter, after some final rescaling by some factors of square root 2, we get that P minus corresponds in field theory to delta minus J. And P plus, sorry, yeah, here is P plus, not P mu, excuse me. P plus to delta plus J over R squared. So now, if we consider strings moving on the PP wave, then, well, anything, not just strings, particles moving on the PP wave as well, should have finite P plus and P minus, right? These are the momenta for things moving on the PP wave. But then that means that as I take R to infinity, in the field theory, delta minus J and delta plus J over R squared must be fixed, which means that delta is of order of J, and both are of order of, is approximately equal to J, and both are of order of R squared, so R infinite. So J is infinite, which means the Penrose limit corresponds to a large R charge limit in AdS CFT. But then what does R squared goes to infinity mean? And specifically, what does, more precisely, what does delta minus J fixed mean and delta plus J over R squared fixed mean? Well, R squared over alpha prime in field theory is square root G squared N, G squared Yang-Mills N. So that means that what I'm keeping, right? So I'm keeping field fixed delta plus J. So but delta is approximately equal to J. So delta plus J over R squared or J over R squared, right? But R squared is square root G squared N. So what I'm keeping fixed is really G squared Yang-Mills N over J squared, right? G squared Yang-Mills N over J squared is being fixed. So what do we obtain then for these strings moving on the PP wave? I've written for you the Polyakov action, which is just a two-dimensional massless scalar action in flat space. So dx, these things with in red in here. But then in the case of the PP wave, I have this particular, so the metric has this mu squared xi squared. So the dx plus is multiplied by mu squared xi squared. But then if I choose the light cone gauge x plus equal to tau, which is needed to obtain physical degrees of freedom for the string, then this dx plus becomes 1. And I'm left with mu squared x squared. So the in the light cone gauge and also conformal gauge, as we described before in previous lecture, so the string action becomes this free scalar x dot minus x dot squared plus x prime squared, but then plus a mass term, mu squared x squared. So the equation of motion for this now massive scalar is the wave equation with the mass term and with the ansatz, with the standard ansatz that the variable is proportional to E minus I omega n tau plus I kappa sigma, we get that omega squared is kappa squared plus mu squared. And kappa squared, now we're talking about closed strings, so momenta around the closed direction is quantized. Kappa n is some n, but there's some rescaling, so it's actually n over alpha prime, over alpha prime p plus, excuse me. So then omega, which is an energy, an eigenenergy, becomes square root mu squared plus n squared over alpha prime p plus squared. And mu squared is the thing that appears because of the pp wave. Otherwise, we would have the result in red. So the light cone Hamiltonian, the Hamiltonian for in this light cone gauge for the string becomes then just a sum of oscillators. We saw that the string is just a sum of an infinite sum of oscillators. But the masses for these eigenenergies for these oscillators now are changed. So in this light cone formalism, where the Hamiltonian corresponds to P minus, and then in turn that is delta minus J in field theory, and the energy E in string theory. So this is equal now to the square root of, one also obtains that P plus, as we saw, is J over R squared. So replacing that inside the square root, we get that the result is square root 1 plus G squared N over J squared times this level N squared. So this is now the formula for delta minus J in super-Yang-Mills that we must obtain. So this was derived from the eigenenergies of the string, which are given here. But now we've turned these into quantized values for delta minus J in super-Yang-Mills. So how do we obtain that? Well, so delta minus J, you see, is 1 plus more, right? Is square root 1 plus more. And this more depends on some little m. But if I put little n to 0, I at least supposed to get the 1. Okay. But besides these, we also have the vacuum, right? The vacuum has delta minus J equal to 0, has no energy. And then the other oscillators have delta minus J equal to 1. So we must obtain things that have delta minus J equal to 0 and things that have delta minus J equal to 1. And we can, and we do, in fact. So if we consider the field that contains the scalar in the 5 direction and the 6 direction, sorry, phi 5 plus I phi 6, or rather x5 plus I x6 is called Z. Then this is charged under J with, by definition, charge 1. And so delta minus J is 0. And all the other phi's have no J, so delta minus J is 1 for them. And moreover, if I take a coherent derivative and act on Z, that also has delta minus J equal to 1, because Z has delta minus J equal to 0 and the derivative delta minus J equal to 1. There's also some fermions and so on, but the important thing is that there are 4 phi m's and 4 d mu z's, so 8 oscillators with delta minus J equal to 1, exactly like we wanted from here. So then to construct this making gauge invariant operators, so a trace of something, but of what? Well, of the z's which have delta minus j equal to 0, right? So the vacuum is trace z to the j because then this has j units of r charge, or in other words, j units of p plus on the string theory side. And if I put this little n equal to 0, as we saw, we had these 8 guys, 4 scalars phi m, and 4 derivatives on the scalar z. And then there are some also some fermions. And at the excited levels, which means n greater than 1 or equal to 1, we can add to these excitations, we can add a momentum, a discrete momentum around a circle, which is this factor, e to the 2 pi I n x over L. And so all in all, when acting with a creation operator for one of the string excitations on the string vacuum, what we do is inside this trace z to the j, we insert what? The phi, one of the phi's. Here I wrote phi 4 with this momentum wave function e to the 2 pi I n L over j. So this is the map between string states and operators in super-Yang-Mills. The operators have been afterwards called BMN operators after us. Now, the only other thing to note is that we have considered here only one and maybe a few A daggers and correspondingly few insertions of the phi's inside a very large number of J's, of Z's. So that is the so-called dilute gas approximation, where we only have a few, impurities, meaning some fields that are not Z's, among a sea of Z fields. So this is a dilute gas approximation, and this dilute gas approximation corresponds to the PP wave in the gravity duo. So now let's step back and think a little bit on why were we able to obtain these results from super-Yang-Mills. So why did we obtain matching actually between super-Yang-Mills and the PV wave? Because it's unusual. We said that when one side is perturbative, the other side is non-perturbative. And it is so. Namely, we were considered the perturbative gravity side and the non-perturbative super-Yang-Mills side, meaning G squared n was fixed and large. But the essential point was that there was a small parameter, which was G squared n divided by J squared. And that was so only for this subset of operators, the BMN operators, even though the full theory still has large Hopf coupling, large G squared n. So it's still, the full theory is still non-perturbative, but it's just this subset of operators which is perturbative. That allows us to calculate things on both sides and match them. But as I said, this is the first step considering strings on the PP wave. Here there were just free strings. But this is the first step towards a quantum gravity description in anti-de Sitter. Then we would have to introduce interactions. This is possible to introduce strings splitting and joining, so interactions of strings perturbatively. Of course, what one would want in principle is to introduce them non-perturbatively. But so the goal would be to connect perturbative superangles with non-perturbative strings, which would really be quantum gravity. However, the point is that one would need to understand how this perturbative superangles is mapped to the non-perturbative strings, meaning what's the definition of the non-perturbative strings? That's how we would learn about quantum gravity. So, you know, on one hand, you could just say, well, if you believe AdS CFT at all couplings, as we've shown that it's true by a variety of tests, then you just define non-perturbative quantum gravity as being perturbative superangles. But that's not very useful because it doesn't tell you how you map it, right? It doesn't tell you, you know, what are the observables in the non-perturbative quantum gravity and how they are obtained. We will, however, show you, we will, however, see in the next lecture one example of that, namely holographic cosmology, where we have some non-perturbative quantum gravity obtained from some perturbative field theory, but with a caveat that it's in a phenomenological approach. But as we saw, this phenomenological idea is already used for condensed matter, so might as well use it for cosmology. So, but that's in the next lecture. For the moment, I just want to continue a little bit and describe what happens. I mean, how is it possible to obtain these perturbative strings from superangles? Just a few more ideas. So, how do we obtain the string action from superangles? So we've seen how to obtain some eigenenergies. But it's nice to see how to obtain the action itself. Well, so the boundary of AdS5, the AdS5, we said it's a cylinder. So the boundary, it's also a cylinder. The real line corresponding to time times an S3. But there's a conformal mapping between R cross S3 and R4. So at least in a conformal field theory, we can talk about either. But if I talk about R cross S3, one thing I can do is Kaluza-Klein reduce on S3 and talk about just a pure quantum mechanical theory, a theory defined just on time. And so reducing on S3 means keeping just the lowest excitations on S3. So for every field, which was defined in 4 dimensions, or in other words, in R cross S3, after the reduction on S3, I talk about a single quantum mechanical object. So quantum mechanical object means in particular A and A dagger. So for each field, I can consider a creation operator. That means that for the constant, for the reduced part, the constant part of the field Z, I can consider a creation operator B dagger with matrix indices. And for the other ones, the ones that I insert inside trace Z to the J, I consider creation operators A dagger, also with matrix indices. That allows us to obtain a map, a more precise map between states and operators, where I talk about A dagger at position L as being a string of creation operators corresponding to the field theory operator, So instead of trace z to the L phi z to the j minus L, I now have trace b dagger to the L, a dagger, b dagger to the j minus L, and now acting on some vacuum. So this allows us to map the BMN operator, the gauge invariant operators, to these states with creation operator at some point. So then the next step is to define a Hamiltonian acting on these states. How do we define that? Well, we start with the Hamiltonian acting on the fields. So on the quantum field theory fields. So the interacting Hamiltonian for the quantum fields is this, trace phi commutator phi squared. And we restrict, let's say we restrict to the fields defined as in here, so z and phi. And then we have trace z commutator phi with z bar commutator phi. And then further restrict this to the creation operators, to a dagger and b dagger. And so we have b dagger commuted with phi, by which I mean a plus a dagger over root 2, and then b commuted with phi, the same. And how does this act on the states? Well, the action is done through Feynman diagrams. So you think of so the Feynman diagrams for the 2-point function, and then with interactions in between them. So like in here, I wrote an interaction, a 4-point interaction corresponding to this interacting Hamiltonian. And the interaction is for fields O, which have 1 phi insertion. So one point about this is that we are in the 't Hooft limit, meaning n goes to infinity, g goes to 0, such that g squared n is fixed. In this limit, Hooft showed that we only keep planar diagrams. So the only diagrams that are left for these 2-point functions I wrote here. I described here. So there are 5 diagrams. Well, and the relevant ones that I want to talk about. So at one loop, sorry. 5 diagrams. So the tree diagram is in A, and then 4 diagrams in one loop in B, C, D, E. And D and E are some renormalizations that can be understood without actually calculating them. But B and C have the interpretation, as you see, the phi is at position L plus 1 down in B, and at position L up. And then in C is the other way around. Phi is at position L down, and at position L plus 1 up. So it means that these Feynman diagrams correspond to hopping from L plus 1 to L and from L to L plus 1. All right. So after a calculation, then one finds the Hamiltonian where so a Hamiltonian that is supposed to act on the states that corresponded to our operators. So a Hamiltonian for action on these A dagger L's. One finds that is like this. So there's some free Hamiltonian, free oscillator Hamiltonian. A dagger A plus A dagger over 2. And then some interaction, which can be written in terms of these phi's. Remember, phi is A plus A dagger over root 2. So phi j minus phi j plus 1 squared. But you see exactly what this means. Phi j minus phi j plus 1 squared is the discretized derivative squared. And if I consider that the free part of the Hamiltonian is, so this is a Hamiltonian for oscillators, so it's just phi dot squared plus phi squared. So the resulting continuum version of for this Hamiltonian is phi dot squared plus phi prime squared over 2, which is just the light cone string on the PV wave. So just let's back a little bit to remind ourselves why. So this was the action, right? From the Hamiltonian, we just switch the sign of x dot squared. So remember, for the action, we had the coordinate x's of the string were just free two-dimensional scalars. And then because of the VP wave, we got the mass term, which was this x squared. So indeed, we get this Hamiltonian for the string on the PB wave. And this is the same that we obtained from the Super-Yang-Mills. So that means what? That means that we've obtained the string then as a discrete so-called spin chain, if you want. So there's some discretized coordinate, right? With capital J positions, right? Capital J sites. And at each position, we have, in principle, we have one of these. So we have, at each position, we have these B daggers or A daggers. But it's just that at most of the positions, we have B dagger, and only once in a while, we have an A dagger, which is this dilute gas approximation. And so correspondingly, if you think of this as some sort of spin chain, at most sites we have so-called spin up for B dagger, and only once in a while we have a spin down for A dagger. And remember, A dagger corresponded to the string oscillators, right? So that means the string oscillators just flip the spin on this spin chain. All right. So one observation is that after diagonalizing the Hamiltonian, the eigenfrequencies are indeed the one that were obtained before. It's just that a little bit more general. So what we obtained before was where we replaced this sine squared with this small argument approximation. So pi squared n squared over j squared. But here we obtain a little bit more general formula. And the diagonalization of the Hamiltonian written here, up here with A daggers. Then the diagonalization corresponds to writing these eigenmodes written in here. So we write a Fourier transform and then some sums of these guys. And when we when we see what that diagonalization does to the BMN operators, we obtain objects of this type. So as I said, for little n much smaller than j, when this argument pi n little n over j is very small, we obtain the string on the PP wave, which has g squared capital N little n squared over capital J squared. But we also get a match when little n is of the order of j. However, not to the PP wave, which was the Penrose limit of AdS5, but a rather different limit of AdS CFT. So this more general result, it's still a result within AdS CFT. It's just a more general result than the PP wave limit. But the interesting thing that I am still not sure what it means. I have some ideas that I've expressed in some papers, but it's not completely clear, is that omega n, this formula, is an all order in the 'T coupling lambda g squared n. Even though the Hamiltonian self was proportional to lambda, the interacting Hamiltonian that I used was proportional to g squared. So in some sense, the result should have been one loop. So, so that means that somehow this result for omega resums all these one loop interactions in a way. The result is not completely general, of course. It's only true for few impurities. Or in here, I considered only one impurity, only one excitation. But yeah, otherwise the result is general. And so to summarize, we have obtained a relation between a we have obtained a relation between the Penrose limit of AdS5 cross S5 and a large charge limit in super-Yang-Mills, and then further a spin chain limit for this super-Yang-Mills. So now this spin chain was only in the dilute gas approximation, so for only a few excitations. But it was proven later that it's actually not necessary to consider just the dilute gas approximation. You can still consider any excitation you want. But to be more precise, I want to show you a little bit what happens if I consider just two variables, one z and one w. So the z was a complex scalar, and consider just one another complex scalar. So then these so-called SU2 sector has objects corresponding to spin up and spin down, as we said. But now we consider operators that contain any number of z's and w's, which means any number of spins up and spin down. And again, we look at the interacting Hamiltonian and consider planar one-loop diagrams again, and find that this can be written in terms of the permutations of the sites L and L plus 1. Well, one can generalize this to higher loops. It doesn't matter, but the point I wanted to make is, so one can generalize to higher loops and consider the more general definition of the Hamiltonian in terms of so-called dilatation operator. it's not really important at this point, but what I want to say is that if you consider this very precise definition, then still this one loop Hamiltonian is nothing but the Heisenberg Hamiltonian for the rotationally invariant, or XXX, spin 1/2 chain. So the well-known Hamiltonian with sigma j dotted into sigma j plus 1 summed over j. So this can be rewritten in terms of permutation and identity. So that means that really from n equal 4 super-Yang-Mills in this large charge limit, we obtain a spin chain, a well-known spin chain, the spin chain of Heisenberg, that was solved in particular by Bethe, and he had used in the so-called coordinate Bethe ansatz, defined these so-called magnon excitations, where you have this, let's say, spin down traveling in a sea of spin up. And the excitations have certain energies, so you can write a wave function that is an eigenfunction of the Hamiltonian with an eigenenergy written here as sine squared of the momentum over 2. And well, yeah, one can consider higher states with more magnons. With 2 magnons, it gets more complicated. The wave function contains so-called two-body S matrix, and which is defined in terms of these objects U called rapidities, or in the case of a solution, Bethe roots. But the point is that the energy in the end is nothing but the sum of the individual energies of these magnon excitations. So, like for the string on the PP wave, where we just sum individual energies of string excitations, also for this spin chain that corresponds to it, we sum the energies of excitations. And I think that is everything I wanted to tell you today. And next time I will consider I will talk about holographic cosmology, which, as I said, is the one example that we know. And well, it's not yet very well defined, but it's an important example, I think, in which we define a quantum gravity, a non-perturbative quantum gravity theory or cosmology via a perturbative phenomenological super-Yang-Mills theory. Thanks.
Thank you very much, Horatiu. Any questions? Either you can unmute and ask, or write down in the chat. Anything is fine. Okay, so while others are preparing for the question, maybe I will ask one or two. What can we learn about the Yang-Mills mass gap problem from AdS CFT?
What can we learn about it?
Yes. Can we solve this in some supersymmetric versions of it? Maybe n equal to 4 super Yang-Mills.
Yeah. So as I said, unfortunately for the moment, we don't have not even QCD, but even large n, SUN at large n, and with one supercharge, so n equal 1 super Yang-Mills. Not even that do we have an actual gravity dual, so precise. What we do have is, of course, a bunch of examples where we have confining theories that have some mass gap. So we have examples of those, but unfortunately, in most of those examples, we have a nice theory that we would like, and then a tower of Kaluza-Klein states that we cannot decouple. So yeah, that's the standard story, and we are not able to go beyond that at this point. I mean, we could say these general ideas, you know, that if you have a theory with a mass gap, you should add a certain gravity dual and so on. But you know, it's not. For the moment, we cannot say anything about the mechanism, because we don't have a mechanism in a theory that is sufficiently close to QCD. We just have we just know how to do things in theories that are still sufficiently far from QCD. So they're confining, but that's about it.
Mm-hmm. How does this mass gap translates to the other side, to the CFT side? I'm sorry, to the gravity side. Like, how does it show up?
Yeah. So that is easy, right? That is easy. That, as I was saying, they're basically, so the mass spectrum corresponds to also a mass spectrum. It's just a spectrum of states in modified AdS.
Mm-hmm.
And the simplest way to obtain a discrete mass spectrum for AdS is off at some R minimum, as I was saying. Mm-hmm. And then all the other examples with mass gap, basically, I mean, well, not, I shouldn't say all. Most of them are, so the ones that correspond to some discrete set of tower of states correspond to just putting, to just smoothly ending the space at some R minimum, where the warp factor is still finite. So yeah, but however, there are examples where we also have, so there's these funny examples where we have a continuous spectrum above a mass gap. So that's something that was you know, at least unexpected to me. I'm not sure how much people expected from the point of view of lattice.
There is a mass gap, but later you have a continuous spectrum, not the discrete one, right?
Yeah.
Okay.
So that's an example that is somewhat confusing. But in most examples, you have a discrete tower of states above a mass gap. Yeah.
Anybody has any questions, guys? It's your chance to ask any questions about AdS CFT. Go ahead.
You also mentioned at some point that to get rid of the supersymmetric part in the holographic theory, you should deform well the sphere, the hidden sphere that you have.
That's one way. I mean, there are many ways, but that's a so that, sorry, I should have said that reduces supersymmetry. It doesn't get rid of.
Okay. And what is the status of getting rid of supersymmetry, or what would the holography would tell us of theories without supersymmetry?
Well, I mean, you know, on one hand, you can invent some situation that is not supersymmetric. It's not particularly hard. I mean, there are many such examples. The problem is twofold. It's so you can write the gravity dual from a system of branes that is not you know, decoupling limit and so on, that is not supersymmetric. But then you don't know much about the theory, and you also don't know much. You don't have a good handle on the holographic map. So it's, you know, the usual story. It's the usual story. The closer you get to your goal, the less you know. So yeah, I mean,
okay.
Yeah.
Any questions? If not, I will ask one more question. You mentioned the Lipschitz scaling, right? So this is on the CFT side.
Yeah.
So what is the gravity dual of these Lipschitz like CFTs? Is it
Sorry,
Lipschitz gravity?
sorry, I missed your
Oh,
question.
okay. You talked about the Lipschitz scaling in condensed matter physics, right? So we have this on the CFT side. So what's the gravity dual of these theories? Could it be Horatiu-Lipschitz gravity?
So people have, so as I said, there are two lines of thought on how to obtain non-relativistic systems.
Mm-hmm.
And I showed you just the standard one, which is to just write a solution which doesn't have Poincare symmetry.
That's correct. Mm-hmm.
Right. So, but it's a solution to a relativistic gravity theory.
Mm-hmm.
But yes, there are people who consider also the other side, is, you know, considering non-relativistic gravity, something like Horatiu-Lipschitz theory, or something else, some massive gravity, or actually massive gravity works better in some sense.
Really? Okay.
Because of massive gravity work better, people have introduced that. I think anyway, I forget right now who are, but so the topologically massive gravity is the example that that seems to work best. But the problem in these cases is it's a little bit harder to define the mapping, right? Because you cannot, I mean, you don't have the decoupling limit of a system of brane anymore, and so to guide you on how to obtain a holographic limit. So in this case, it's yeah, it's a little bit unclear, at least to me. So.
There was some paper about this holographic mapping between Lipschitz theories on the CFT side and the Horatiu-Lipschitz theory by Melby, Thompson, Hojawa. But I don't know if they definitively established anything or just attempted to study.
I don't think, well, I've seen that there were not too much follow-up. So as I said, people have been.
But I never thought that topologically massive theories are as the duals of Lipschitz theories on the CFT side. That's interesting. I'm gonna read something about it. So, any other questions? Any other questions? So if not, you can watch this video once again, and then maybe read Horatiu's book on AdS CFT, and you can ask all the questions you have in the next lecture, right? So with this, let's close for the day, right? So thank you so much, Horatiu. See you next week.
Bye. See you.
See you. Bye-bye.